Greetings, I am Chris Kennedy. Today's lecture in space engineering is about human system integration and well building design. So, what is human system integration? It is a strategy to incorporate all the human system requirements as part of the triangle we talked about, hardware, software, and the human, and making sure that we understand the human's role in all aspects of the mission, the design, and the spacecraft and interactions with the various components of the system. So it starts with an understanding of NASA's human system integration experience, which then led to development of an incorporation of that experience into the NASA systems engineering process and requirements and program and project managers handbook. So this process has allowed human system integration to be incorporated into NASA procedural requirement 7123.1b, system engineering HSI plan needed for spaceflight programs. This is an important step. And in 2015, they updated the system engineering handbook to include this. Um, Also, NASA developed the Human System Integration Practitioner Guide. So as you can see here, the revision B in 2013 incorporated human system integration. And then there was a major update in 2014, which was published in 2016 on the NASA System Engineering Handbook. And I recommend that you get that. And it's in my references as well as the Human System Integration Practitioner Guide. NASA did back in the 2010 timeframe, they did some benchmarking with the DoD to better understand human system integration from the perspective of how the military does it. And what it did is it opened up our eyes to an understanding we need to be more formal and more cognizant about human system integration. So let's talk about the human system integration in context. So human system integration, or HSI, is a system engineering discipline. So it's a part of that system engineering process that applies knowledge of human capabilities and their limitations, which is important, throughout the design, implementation, and operations of the hardware and software. So the human in the HSI refers to all personnel involved within a given system, including users, operators, maintainers, assemblers, ground support personnel, logistics suppliers, personnel trainers, pretty much everybody. And HSI embraces the concept of the human as a subsystem on par with hardware and software. An interdisciplinary and comprehensive management and technical process that focuses on the integration of the humans considerations into the system acquisition and development process to enhance the human design and reduce lifecycle ownership costs and optimize total system performance. And so this is really important. It's part of the thinking like concurrent engineering, where you include folks from the manufacturing, from the assembly, from maintenance to better understand how to develop and design your systems to be operated by humans or with humans in the loop. This is a very important part because even though NASA has been flying astronauts since the 60s, 1960s, for over 50, 60 years, it is still important to be very uh, methodical about inclusion of the human as a system. So the HSI discipline includes a range of managerial and technical domains and specialties. For example, system engineer, program managers, NASA institutional support offices, human factors engineers, safety and reliability analysts, psychologists, and medical professionals, logistics, and maintenance expertise. The HSI domains collectively define how human capabilities or limitations impact the hardware or software of any given system in terms of its design, effectiveness, operation, support, and the associated costs and affordability of these components. And two, how the system hardware and software and environment impact human performance. So it's just as important as part of thinking about the concept of operation is understanding the human role, and the human performance within this system. An important part of this is that these roles and responsibilities must be identified in the human systems integration plan at the outset of a project. And so the human system integration plan is now required by NASA projects and programs as part of the early documentation. How are you going to address the human? So this is a forcing function to force all contractors in NASA to really apply these techniques and methodologies of human system integration across the NASA systems engineering process. So from the standpoint of concept development, participating early and to ensure HSI considerations are included in conceptualization. In other words, functions allocated to the humans, support analysis of alternatives, flight, ground crew projections, human risk assessments. It's part of the requirements definition to better understand being a vital part of the human and capabilities and specifications in that requirements definition process, to write clear, concise, and testable or verifiable HSI related capabilities and specifications to ensure that the human allocated functions and risks are addressed. It's included in the design development, participation in the design process of systems to ensure HSI principles are incorporated into design decisions, as such that system trade-offs do not marginalize human considerations. Important aspect of this and examples is ISS. There are many aspects in the ISS that had to be redefined, and redesigned related to interactions with humans in the ISS research platform, and even logistics from that standpoint. So testing and evaluation is another aspect to conduct verifications of HSI related system requirements and validation in their operational context, and as part of sustainment. So the continue of the system support process to ensure HSI concerns are addressed throughout the operationals, lessons learned, engineering changes, and training improvements. So ISS, the research laboratory in low Earth orbit, is in a sustained operational mode. And as such, we are continuing to better try to define and improve the HSI concerns. So human system integration, there are numerous domains as part of this. The human factors engineering, which is designing hardware and software to optimize human well-being and overall system safety, performance, and operability by designing with an emphasis of human capabilities and their limitations. There's examples of expertise, crew workload, usability, human in loop evaluations, human error analysis, human interface, system design, and human factors engineering analysis. There's operational resources domain, which is the considerations and resources required for operations planning and execution. And you can see the examples of expertise and the kind of work that they do, the tasks. There's maintainability and supportability domain that has to be addressed and looked at and understand to design to simplify the maintenance and operations from a human resource perspective, including the spares, consumables, and logistics, aspects of maintainability and serviceability, your assessment of reach and sustainability and housekeeping and maintenance and repair. You have the habitability and environment, external and internal environment considerations to be considered and look at from the standpoint of the human habitat and exposure to natural and induced environments and the living and working conditions. So the physiological and psychological well-being of the crew, the human, You have it obviously from the safety, because it's so paramount and so important that the safety is considered of the human throughout all mission modes and mission through the mission design reference mission. And then training, training the humans to both from the standpoint of manufacturing, assembly, integration, testing, operations, and disposal. So, I was part of the human system engineering or human system integration work and support that happened during the Commercial Crew Program. Specifically, I worked on the Sierra Nevada Corporation, their vehicle design, but also then later on was part of the analysis and work that we did through the Human Health and Performance Directorate for Boeing and SpaceX vehicles. And this was one of the first programs that was a forcing function that required that the program have a human system integration plan. So let's talk about the human system integration practitioner guide. And this is important. And so I'm going to give you a kind of a high level overview of the contents of the practitioner guide so you have some familiarity with it. In the future, you probably should go ahead and look at this and study it a little more. As part of your knowledge and skill gaining here at CICSA, we want you to better understand the practitioner guide and how this fits into it all. So the practitioner guide is captures the HSI best practices as applied to the NASA systems engineering process. So its goal is frequently used document focused on HSI leads and team members. It's written to sync up with the recent HSI content and the new systems engineering handbook. It provides HSI layers to the 17 systems engineering engine process and life cycle methodologies. So it's a it seamlessly integrates with the systems engineering methods and tools. The practitioner guide reader should be familiar with systems engineering handbooks, so because they work hand in hand. It provides a how-to guidance and tailors for project sizes and targets a wide variety of the user roles, and much more detailed and comprehensive than the HSI content in the systems engineering handbook, and is written at the agency level with goal of added robotics and aviation into the future. So the Human Systems Engineering Practitioner Guide has 4 key concepts identified. define an effective HSI effort. The system comprises hardware, software, and the human elements, which we talked about. The human interactions that need to be considered in program and project management, systems engineering, and HSI include all personnel that interface with the system. So that includes the end users, the pilots, crew members, maintainers, ground controllers, logistics, personnel, sustained engineering, etc. And successful HSI depends upon integration and collaboration of multiple domains. And HSI must consider and establish this in the program and project planning guide early in the system development and acquisition. So here's the guide outline. You have chapter 1, which is introduction to human system integration. It's kind of the why, the background, the key concepts and domains. Chapter 2 is implementing HSI, the who, the authority, hierarchy, the documentations and collaborations. Chapter 3 is HSI in the NASA systems engineering, when and what, by phase. And chapter 4 is planning and execution, the how, getting organized, tailoring for a program or project size, planning for HSI and the key skills. And the thing about tailoring and also the systems engineering process is the idea is for programs and project management to tailor to the size of the project. So not necessarily everything fits one shoes per se. So you want to look at a program or project, size it up, and decide how to tailor the systems engineering effort and the human system integration effort. And then chapter 5 is the body of knowledge. It's a list of HSI information from NASA, DoD, and other sources. And then there's the appendices, which gives you an plan outline, a planning checklist, and implementation experiences. So why is this important? And chapter 1 talks about the introduction to HSI and the whole idea about, you spend 8% of your budget in the pre-phase A and phase A concept development, but you're committing cost, quite a bit of cost to the committed life cycle. But when changes are made back here in your phase C, final design and fabrication, the cost to change that is, from 20 to 100 times or even 1,000 times. So the idea of getting early on and getting some of this right related to human system integration, like systems engineering, is so important that the lifecycle costs of a program or project are locked in early in programs and projects. So it's important to do a really good job up front in your pre-phase A, phase A, and phase B design definition. So hardware and software system designers tend to focus on technology development without considering the human interaction or human integration in the system. And I've seen examples of this numerous times. And so when we did the Habitat Demonstration Unit, one of the aspects of that was addressing human system integration and human in the loop testing and forcing these hardware and software technology development projects to get off the benchtop and integrate into a system test, which included the humans. So chapter 1 continues to talk about the HSI process approach and identifying the HSI as a cross-cutting function provides HSI structure for the whole system engineering effort. And there's multiple benefits of this approach is that the system engineer can readily learn to be a HSI practitioner. They have a lot of the right skills and tools, and it's a matter of concerted effort to make sure human-centered design practitioners learn these systems engineering best practices and follow that. And the second benefit of this approach is directly to the program and project stakeholders to ensure that the original operational vision is fulfilled. And the third benefit is immediate application of HSI practices to systems engineering workflow. There are a number of NASA policy directives and procedural requirements that have HSI content. So you have the NASA SP 2007 6015, which is NASA Systems Engineering Handbook with a 2015 update that talks about and describes how systems engineering and development and implementation of large and small project and programs, and includes description of HSI domains and lifecycle activities, products, procedures, and practices. The NPR 8705.2b, the human rating requirements for space system, includes HSI aspects within their updated program procedures. The NASA System Engineering Process and Requirements has Appendix A and Appendix G, which addresses this HSI plan, HSI definitions. The NPR 7120.5E, NASA Space Flight Programs and Project Management Requirements, establish the requirements by which NASA formulates and implements space flight programs and projects, and consistent with the governance model contained in NPD 1000. Also, the NPR 7120.11, NASA Health and Medical Technical Authority implementation, directly talks about responsibilities to ensure agency health and medical policies, procedures, and HSI is included, as well as the NASA health and medical requirements for human space exploration. So these procedural requirements are important aspects that get incorporated into the overall missions, making sure that human system integration is covered. Also, there are additional documents and standards and handbooks. There's the NASA Standard 3001, NASA Spaceflight Human System Standard, Volume 1 and Volume 2. Volume 2 really talks about the aspect of human-centered design and habitability. There's also the Human Integration Design Handbook, HIDH. Then there's also the Human Integration Design Process, as well as the NASA Spaceflight Program and Project Management Handbook. So these are all important aspects of how the HSI gets implemented and put into the procedural requirements for human spaceflight system design. Chapter 2 talks about implementing HSI, the aspect of concept development, requirements definition, design development, test evaluation, statement, and different aspects of when or how to implement into and where it gets implemented into the different design phases. Chapter 3 is really incorporating how the HSI is incorporated into the NASA systems engineering engine. A depiction of HSI product inputs and outputs from the systems engineering process using the NASA SP 2007-6105 wall chart process flow diagram shows the figure here that the systems engineering engine with HSI inputs and outputs. So you can follow through the technical process from the standpoint of how system engineering through the process that we've talked about and the different aspects of human system integration be incorporated into this. So as you go through the process that we had talked about for design of hardware and software, you are also doing this process from a standpoint of human-centered design, human system integration. And you can see the process flow here, and then the cross-cutting processes on the right side. This is a kind of a description of that aspect of the system design processes and the HSI emphasis. I'm not going to read through all this, but it is important for you to, as you look through this, as you go through the different processes of system design, product realization, and then technical management, how the HSI aspects are incorporated into the different pieces of it. From the standpoint of functional allocation between systems and humans, understanding the base in the concept of operations, how the humans are incorporated to that, the functional allocation, operational goals, et cetera. And then when you get into the product realization, the aspect of validating the design for all human system interactions and human in the loop testing validation of the concept of operation. Chapter 3 also talks about the different products and at the different phases and at the different, whether it's a draft or an update or your baseline. Here we talk about more of specific on the phases, pre-phase A, B, C, D, and E. And we've talked about what those are previously. And then it gives you a little bit of the guidelines on the aspect of development and refinement of the HSI plan. So in pre-phase A, phase A, you develop the HSI plan based on the results of the functional analysis and derived human-centered requirements, plus the concept of operation. And you can see in each one of these phases, you can read through how you would incorporate or some of the things to look for. This is the HSI plan outlet content outline, excuse me, and it walks you through the outline of an HSI plan, the planning and execution of an HSI plan. The appendix shows the HSI plan content from the standpoint Appendix A, and you can walk through the phases again, of the description of each of the phases and the kind of HSI related products, activities, and risk mitigation that you would perform. So this is a good checklist. These are representative examples of HSI tools that are used during the various processes and during the various analysis through the various design cycles. They have human error analysis, workload analysis, usability analysis and evaluations, anthropometric analysis, task analysis, requirements management, uh, lighting analysis, acoustics, radiation, etc., and the physiological analysis, as well as you really want to do psychological analysis of the design to see if it benefits and supports the well-being of crew. And these are specific examples of tools that are used by industry. One thing I wanted to bring up when you're thinking about humans in the loop, think about, and part of this analysis is the effects, a human factor effects on partial gravity design. So if you're thinking about designing habitats and so on for the moon or even in space, consider these different positions: the walking, running, posture, jumping, handling equipment, and the differences from Earth gravity as defined here in the center column, and then the habitat design impacts. So things for you to consider: traction of surfaces, corridors should be clear of obstructions and mobility aids, low ceiling heights in personal spaces, higher ceiling heights in circulation or group gathering areas, traction on surfaces, needing restraints, mobility aids, these kind of things. So let's talk about well design. And this is a Earth-based methodology and looking at the aspect of the physiological and psychological well-being of humans working in a building. And so the Well Building Institute has been developed, and there's a link here, to better understand and better define buildings here on Earth. And it's a performance-based system for measuring, certifying, monitoring features of the built environment that impact human health and well-being through the aspects of air, water, nourishment, light, fitness, comfort, and mind. So the Well Building Standard, Volume 1 and Volume 2, is revolutionary or revolutionizing the way people think about buildings. And this is important because this type of standard is something that we will want to incorporate into our thinking as we begin to build facilities on the moon and Mars. And so this aspect of how to design operations and behaviors within spaces where we live, work, learn, and play can be optimized to advance human health and well-being. And this has applicability to development of lunar and Mars facilities, habitats, and such. Well, version 2, sections 10 address air, water, nourishment, light, movement, thermal control, sound, materials, mind, and community. And so it addresses some of the psychological aspects of a building and making a building better to be able to work in and making it healthier and more productive for humans to work in. And you've gone into buildings before and you walked in and you said, wow, this feels great. What is this about this building? It's awesome. And then you've also walked into buildings, you're like, ooh, this is kind of drabby. I don't know. I don't know if I want to be in here or work here. So this is a really important topic to look at buildings and look at spacecraft and look at facilities on the moon and Mars. So here's another link to what is WELL certification. And actually it's a part of and goes beyond what LEED does for architecture buildings because it addresses the aspect of humans. And I've gotten to know and worked with Dr. Christina Banks, who's the director of Interdisciplinary Center for Healthy Workplaces at UC Berkeley. And here's a link to her site there. And as part of that, she really got me thinking about this idea of well and wellness of buildings and how to apply that to space and the space facilities that we would want to set up on the moon and Mars. It addresses design and research methodologies to combine to support health, well-being, and productivity. So in short, the prosperity of people and place. It addresses the physical environment affects human beings. So the physical environment affects the human being, physically, emotionally, psychologically, and socially, whether we design it with that in mind or not. and it addresses the organizational psychology and public health perspective, how this is subsequent of subsequently affects motivation, satisfaction, health, and degree of person environment fit. So she likes to look at it from the standpoint of the Interdisciplinary Center for Healthy Workplaces um, is kind of really a catalyst, a repository, and looks at the different aspects of the law and public policy and employment laws, the work design, engineering, ergonomics, software, automation, the tools, looking at the technology, the health technology and sensors, the built environment, the physical environment, the social impact, societal impact, public health, nutrition, physical activity, demographics, the human nature, the psychology, sociology, and economics, and then the mind and body, medicine and neuroscience, and the work, organizational design, and human resources. So all of this plays into the idea of healthy workplaces. There are 9 needs that human needs that need to be addressed as part of healthy workplaces and well buildings. And so these 9 are the physical well-being, vitality, personal growth. These are the human needs that we need to satisfy to make productive and beneficial spaces for humans to live and work in. Safety, meaning and purpose, positive emotions, belonging, social connection, autonomy, competence and mastery, engagement and accomplishment. So if you address each one of these human needs in a positive aspect, your buildings and your spacecraft or your lunar facilities, habitats, etc., the humans that will be living and working there will be productive and they will prosper. So in the aspect of design environment, um, to secure the need satisfaction. So there's the drivers of need satisfaction in the physical and psychological environment. So the idea of privacy, flexibility, predictability, equity, comfort, connection, and safety. And you can see that how each one of these has specific aspects or characteristics that really is trying to satisfy these drivers. Sally Augustine, who wrote developed the Living in an Impressionist World, Human Experiences of Places, really addressed it from the human emotional experience of the physical environment is shaped by 5 factors: the fundamental universe, sensory processing, individual place, experience, and history, group culture, national culture, and personality. And color, from the standpoint of color for humans, to excel at knowledge, work in a grayish green with a white brightness increases our ability to do work. So color is an important aspect of spacecraft, the interior of spacecraft, or any interior, whether it's a home or an office or a building or a lunar habitat. So environmental psychology is important. Studies of burnout, principally from the decades of work by Christian Massala and Michael Leader. They define burnout as workers who are overwhelmed, unable to cope, unmotivated, and display negative attitudes and poor performance. Well, this type of um, emotion has happened on numerous space missions in the past and on ISS. And so, what we're learning is the very important aspect of the psychological well-being. You may address all the aspects of the safety, et cetera, of a space mission or ISS, but the psychological aspects can break down and then thus put humans at risk. And we've seen incidences on ISS where this has occurred, and we've had near mutiny. It's not reported, of course, but from when I worked at NASA, I got to see and understand some of these situations that occurred. And they were very close to having some real bad situations. And a lot of it is brought on by this psychology, the psychological characteristics or lack thereof in space station. So these authors characterize three phases of burnout: exhaustion, cynicism, and inefficacy. So it's important to know the outcomes of burnout and then the recommendations of how to avoid burnout. So here's your outcomes: poor quality work, low morale, etc. You can read through these. And there's the strategies to strategically address or areas for burnout mitigation: sustainable workloads, choice and control, very important for people, our humans, reward and recognition, super important, supportive work community, fairness, respect, and social justice, clear values, and meaningful work. So these are important aspects to and characteristics to think about how to address the psychological well-being of these long-term space missions. I want to address biophilia because this is an important aspect. Humans have evolved here on Earth, right? And so as such, as we move to this strange environment in space, and strange worlds, Moon and Mars, we need to think of and remember our connection to nature. Humans, so biophilia is bringing nature into the built environment. Patterns found in nature comfort humans because we have grown, we have evolved in nature. So things like wood grains patterns, plants, lighting, art, color, these are all found positive effects on human beings. It stimulates the senses and promotes active psychological and physiological restoration, satisfaction of those basic human needs. So the biophilia hypothesis suggests that humans possess an innate tendency to seek connections with nature and other life forms. So here's the aspect of the uh, what has been produced at Berkeley. They how to build the best workplace for health and well-being and productivity. So hopefully this gives you a glimpse in understanding into the human system integration, human-centered design, and then well building institute, and how importance of the human to be considered as part of the hardware and software, but also the built environment, the psychological aspects and the psychological well-being of humans. Thank you very much. Appreciate it.